Hello and welcome everybody. My name is Dan Price. I'm a software engineer on the developer tools team, and I'm here today to talk to you about debugging OpenGL with Nsight Visual Studio Edition. Thank you everybody very much for coming. So our agenda for the day is really to give you a high-level overview of Nsight and the features it offers. And to do that, what we're going to be doing is we're going to be working with a sample application that we call IslandsGL. Now this particular app is interesting. It was given to us by an engineer who wanted to learn how he could use Nsight to debug some problems that he was seeing with his application. So what we did is, we took a look at it and we thought it would be a great application to use as a case study for Nsight. And there are a number of things that we're going to be doing today. Basically where we're going to start is we're going to just start by debugging a CPU-based implementation of a water simulation, and I'll tell you a little bit about that in just a moment. Then what we're going to do is we're going to look at taking some pieces of your algorithm off of the CPU and putting them on the GPU and seeing what sort of problems we may encounter along the way. Again, really what we're looking to do here is to give you an overview of what Nsight offers in terms of OpenGL debugging. Nsight does offer CUDA debugging, Direct3D. Today's focus is on OpenGL. We do have a profiling webinar next week, which we will talk more from a performance perspective. There will be some talk of performance today, but today's approach is primarily looking at debugging. And the two aspects we're looking to discuss are our frame debugger and our shader debugger. Our frame debugger basically presents you with a way of scrubbing through all of your draw calls to see how each contributes to your scene. And a shader debugger basically gives you the ability to dive into your shaders, analyze variables, understand what's going on, and I'll be demonstrating that all as we proceed. Again, the application we're going to be working with today is called IslandsGL, and basically this application simulates water from the ocean using Tessendorf's algorithm. Now this is a well-studied algorithm. It's been used in movies from Titanic to The Life of Pi. It does model a fully developed sea state. What's interesting about this particular algorithm is that the workhorse of the algorithm is an FFT, and currently this is implemented on the CPU. A little bit later we'll be looking at moving that over to the GPU, but some notable pieces of the FFT is that it does use both the forward and inverse FFT for both heights and chop, and initially uses 128 by 128 resolution patches. We'll be looking at what happens when we increase the resolutions of our patches for higher fidelity. So this algorithm does have a couple of interesting features. It offers per pixel reflection and refraction, models for null factors, and basically does do a nice caustic simulation so that you can see both several orders of effects of your waves from from your chops, as I mentioned before, to this sort of blurriness that you will see inside of the water. So the way that this algorithm is implemented, it's implemented using tessellation. And as I mentioned before, we have 128 by 128 patches. We are using a height map to simulate this water, and one of the features that this algorithm tries to achieve is a level of detail control. And by that I mean to say that we try to achieve a more dynamic tessellation based on how far you are from the camera. And one of the things we'll see when we do actually run this application is that that's not actually working as it was intended. So we're going to use Nsight to dive in and try to understand, well, why is our tessellation working the way it is, and how can we fix that? So this is basically the scene with all the pieces put together. It simulates both terrain and water and sky, and it's really kind of a pretty picture. Without further ado, though, I'm going to just jump right in. So what I'm going to do is I'm going to start up my first application. So I'm going to build my application so that I can show you all what it looks like. Now this particular application has a Visual Studio project, but you don't actually need a Visual Studio project to run with Nsight. Now you can you can create a dummy project for your own application if you just want to use Nsight within Visual Studio for your debugging. And this is useful if you use a different build tool other than Visual Studio, such as CMake or Make or any number of things. So the first thing I'm going to do is I'm going to launch graphics debugging through the Nsight menu. Okay. So here we are. This is our application. As you can see, we have terrain, we have our water simulation going on, and what I'm going to do is I'm going to tell you a little bit about what you're seeing here. What we have is we have some configurable graphs that will tell you sort of the utilization of the GPU as well as the utilization of individual units or modules on the GPU, as well as some other information. Now, all of this information is fully configurable. I'm not going to show that today, but I'd encourage you, if you do have a chance to try it, see what all the graphs that we offer. There are really quite a lot there that you can really dive in for the exact things that you're interested in. What I'm going to do is I'm going to do what's called pausing the application, and to do that I'm going to bring up the HUD, and what this HUD offers is basically just a way of discriminating between input into Nsight and input into your application. And what I'm going to do is I'm going to pause the application. Now that I'm paused, what you should see is you should see the scene with an animated wireframe and basically a scrubber on the bottom that allows me to scrub between different draw calls in the scene. So I'm going to just slowly scrub this scene. And basically what this is showing you is a representation of all of the API calls that contributed to this scene. Blue is a draw call, green is a clear, and it will show you the current render target for each particular clear or draw call. Now what I'm first going to do is I'm going to inspect how we're actually doing with our tessellation by scrubbing to the scene that renders the water. And what I'm going to do to make this very obvious is I'm going to switch my animated wireframe over to a red wireframe. So I'm going to just scrub. Okay, so here you can see. Now what's interesting about this tessellation is that it looks actually quite uniform across the entire scene. This isn't something that was actually desired. What we would really like to do is to have our tessellation fall off or our level of detail be decreased as we fall off in the distance, because that's not necessary. What I'd also like to do is I'd like to take a look at this from a different perspective. I'm going to resume the application, and what I'm going to do is I'm going to back up so we can get a really bird's eye view of the entire scene. Okay, I'm going to pause my application again and scrub back to that draw call. Now as you can see, the scrubber is really useful for dialing into exactly what you're interested in on a particular scene. So as you can see here, we have some fall off in the distance, but it's not nearly as much as we had before. Basically, we want this to be a little bit more uniform here, because when you have a bird's eye view, you want to make sure that your level of detail is high so that we're not seeing all the patches in our simulation here. So I'm going to take even a slightly more downward looking view. And you can see that we're getting the desired effect. We can't even see the patches at all when we have sort of a top-down view here. So what I'm going to look to do next is to basically show you the shaders that we're using to calculate this particular tessellation here. So I'm going to exit the application so that I'll make it a little bit easier for everybody to see. And I'm going to go to my source code here, to my water shader, and I'm going to scroll down to where I'm calculating the tessellation factor for this particular water simulation. And you can see this function calculate tessellation factor here. Now it's actually kind of a poorly documented function and sort of opaque. It's not really obvious what this particular function is doing. One thing that is obvious is that it is trailing off by the square of the distance, which is desired, but it has several other factors that are sort of static and hard-coded here. For one, we have a minimum tessellation factor of 20. Now that's actually quite high. Additionally, we have this factor of 0.0002 here with really no discussion of what it actually is. So what we'd like to do is we'd like to try to figure out, well, can we improve this function? And how do we improve this function to make it not only more obvious what it's going on, but also to achieve a fall off in the distance, which is something that you're not seeing in this particular shader as implemented right now. So what I'm going to do is I'm going to now move over to an application where we've actually gone ahead and done that. So here we are with an improved version of this particular function. Again, this is just an application that we received as is, and what I'm going to be talking through today is basically some of the modifications we've made to clean up the algorithm, to increase performance, etc., etc. But what's really interesting about this particular case study is that what we're going to be encountering today are actual bugs that we encountered in making this transition. Everybody encounters bugs as they're trying to improve things, and we're going to walk through exactly what we did. So one of the most obvious and notable things about this particular shader now is that there's actually comments. There is far more detail in what this shader is attempting to do. In particular, we actually are now calculating a unit that is a factor of the patch size, and what we are doing is we're actually calculating this in a way that is far more clear. So what I'd like to discuss right now is noting that this particular there's a special factor in here so that when we are looking down orthogonal to the plane, we will have that high tessellation that we still desire, and that is this section of code over here. And you can see that this is basically calculated when the camera is orthogonal to the XZ plane. So with this particular implementation in place, let's see what actually happens. What I'm doing is I'm building the application, and I'm going to start graphics debugging. So as you can see, this is clearly not working as it's intended. We clearly have some bugs. Well, let's see if we can actually use Nsight's shader debugger to figure out what's going on here. So what I'm going to do is I'm going to do local shader debugging, and in order to do that I need to pause my application. So I'm going to go ahead and bring up the HUD and then pause the application. Okay. Now that I paused my application, I have that same view that we saw before, but what I'm going to do is I'm going to switch to Visual Studio to show Nsight's host integration. And what we have here is we have a presentation of the API state of at each particular draw call. I have a scrubber very much like I did on the HUD on the application before, but what's interesting about this particular one is that we also introduce some performance markers which allow you to annotate your draw calls with particular ranges. And you can see we've got shadow map, reflection, etc. So what I'm going to do right now is let's see if we can figure out what's actually going on. One thing I forgot to do is I have to actually scrub to the draw call that is rendering this water. So I'm going to do that. And here we are. Switching back to Visual Studio. You can see that these two scrubbers are in fact linked. When I scrubbed on the application, my scrubber in Visual Studio is updated for that particular draw call. And what I'm going to do is I'm going to go to the shader that actually is running on the GPU by going to the Program tab, and I'm going to go to its source. So we see that same source that we had before, but what I'm going to do is I'm going to actually set a breakpoint here. And the breakpoint I'm going to set is right where we're calculating each of these tessellation factors. Okay, wait a moment for it to be triggered, and we are there. So what's interesting about Nsight's shader debugger is that it works exactly like Visual Studio's built-in debugger does. You can inspect variable values. You can actually do conditional breakpoints. We found that we will be using that later. You can step through code. You can set some pretty complex conditionals, and all of those conditionals are actually evaluated on the GPU. So what I'm going to do right now is I'm going to set a watch on the GL test level outer variable here and inspect its value as this shader is actually executing on the GPU. Okay. I actually had two of them already, so I'm just going to clear one of them. And what I'm going to do is I'm going to step line by line. Okay. So right now I'm just using Visual Studio's F10 key to skip from line to line. So I'm inspecting this first assignment to GL test level outer, and it sets the 0th component to 12.5, stepping through each particular one that follows. I see that it hasn't been updated either. The first component's not being modified. Okay. So what's pretty clear what's happening here is that there's a copy and paste bug. The engineer who implemented this accidentally copied and pasted this GL test level outer assignment, but forgot to update it for each of the components beyond the 0th one. When we have 0, 0, 0, 0, when in fact we should have 0, 1, 2, 3. So what I'm going to do is I'm going to actually let me update this particular code, fix that particular issue, and see what we get. So I'm going to stop debugging with Shift F5, basically using Visual Studio's built-in debugging, and I'm going to modify my source here to update these factors. So 1, 2, and 3. Now I don't actually have to recompile because this is a shader that is compiled at runtime, but I'm going to do it just to be certain, and I'm going to start graphics debugging again from the Nsight menu. Okay. So clearly our rendering issue is gone, and let's see how we actually let's see how our tessellation is looking. So what I'm going to do is I'm going to pause and capture the application. There are two ways to do that. You can do this with the pause and capture frame button over here, or you can press spacebar, and I'm going to be using spacebar because it's easiest for me as a presenter. Okay. Again, switching over to that red wireframe, and I'm going to scrub to that water draw call. Okay. And well, while we fix our issue, this particular implementation doesn't seem to have achieved what it was looking to achieve. It's actually far too dense all over. And again, one of the primary things that we wanted to achieve was to see a level of detail decrease as we went off in the distance. Okay. So what I'm going to do right now is to go back to my shader debugger and see if I can step through my function to see what's going on. I'm at the draw call that I'm interested in. I'm going to my API Inspector, and I'm going to go to my Program tab to show me the currently bound program. And I'm going to click through this link to the source of my shader. This time what I'm going to do is I'm going to set a breakpoint in the calculate tessellation factor function, and I'll set one right about here where I'm calculating this outer test factor. Okay. Waiting a moment for the breakpoint to be hit, and I'm going to set a watch on this outer test factor function, on variable I mean to say. Okay. Stepping over with F10. Okay. See that my factor is just shy of 0.03, and as I execute this next line of code, it is set to 1. Okay, that doesn't seem right. Well, this line over here is looking as if it wants to make sure that outer test factor does not go above 1.0 to basically clamp it at 1.0, but instead what it's done is it's assigned it to 1.0. Okay, so what's wrong here is that we really wanted a min operation. We wanted the minimum of 1.0 and this outer test factor. We want to make sure that it's clamped at 1.0, but we implemented it in the wrong way. So what I'm going to do is I'm going to change this over to a minimum. I'm going to stop my application with debug, stop debugging. I'm going to go back to my shader, go to my source, and I'm going to change this maximum to a minimum. And I'm going to run once again. I'm going to pause and capture the application. Enable my wireframe and scrub to this draw call that I'm interested in. Oops. Okay, so what we're seeing here is that we are having a definite fall off in the distance, which is good, but our close values are not tessellated nearly as much as it was before. So something else might be going on here. Let's see if we can figure out what it is. So what I'm going to do is I'm going to go back to my Visual Studio. I'm going to take a look at this function here, and I see that this outer test factor over here is scaled by this variable g_dynamic test factor. So what I'm actually going to do is I'm going to see what the value of this is in the API Inspector of Nsight. So what I'm going to do is go to the API Inspector and go to my Tessellation Control Shader tab. And I can see that this particular factor over here is set to 12.5. Okay, so that's interesting. Well, this factor is actually used in a couple different tessellation implementations. In particular, it's used for the terrain as well. So I'm going to take a look at what its what its value is in the terrain. And to do that, I'm going to see that I have a performance marker here that annotates the terrain pass, and I'm going to scrub to it. Okay. I can see that this dynamic tessellation factor is actually 25 in the terrain pass. Now that's interesting. Why is it at 25 in one and 12.5 in the other? These should be set somewhat similarly. What I'm going to do is I'm going to actually see where and how this particular factor is being set. Now in GL, the way you change uniform values is by looking up a uniform location and then setting that location to a particular value. So I see here that this dynamic tessellation factor is at location 3. What I'm going to do is I'm going to open up the event window, which shows me a list of all of the API calls that I've had in this particular frame. Now, one thing I should mention about Nsight is that we are implemented and hosted in Visual Studio, so you have all of the docking features available to you that you would expect in your normal Visual Studio usage. And I'm just going to dock this over on the left-hand side. So what I'm going to do is I'm going to filter with this particular window, and I'm going to filter for all calls that update that particular location equals location of 3. So I'm going to search for location equal to 3. And I see here a tree view of each of my calls that match this particular filter. And what's really great about the tool is that I can see the particular pass that each was set within. So I see that in the refraction pass, this was set to 25, reflection 25, color pass 25, but in the water pass, it's set to 12.5. Now that doesn't seem right. It seems like when we went and updated this particular algorithm, we didn't compensate for this factor everywhere in the code. So what I'm going to do is I'm going to now search for where we're actually updating this particular factor by, first let me stop my debugging. And I'm going to search for that dynamic test factor. Making sure I'm searching in the entire solution. Okay. And in the find results window, you can actually see that you can see each of these particular calls, and what's very clear here is that this dynamic tessellation factor is set to half of this other constant here, dynamic tessellation factor. So what I'm going to do is I'm going to now move over to it, and I'm going to remove this halving of this particular factor to see what I get once I do that. I'm going to remove it, rebuild my application, start graphics debugging once more, and I'm going to pause and capture the application. Scrubbing once again to that draw call. Okay, so now this is exactly what we wanted. We see that our level of detail is falling off in the distance. We have a much more detailed, much more dense mesh in near us, and we're achieving those two factors that we wanted to. Let's take a look at the top-down view to see if that's still working the way we want it to. I'm going to resume the application. I'm going to move in and up. Pause one more time. Scrub. Okay, now this is great. You can see that our top-down view is highly tessellated exactly as we wanted, but what's really important is that we don't see any transitions here. We don't want to see those patches. So we've achieved everything that we've wanted to with this particular update to this algorithm. We did encounter some bugs along the way, but we are where we want to be. So what I'm going to do right now is I'm going to just summarize what we talked about. Okay. So where we were is we started with that one-line tessellation factor calculation. We rewrote it so that we can have better units. We actually added some comments here. There were no magic numbers here. There's some bugs were fixed. Basically, the far tessellation and the top-down tessellation were not as desired. Of course, along the way, we did have some bugs, but we showed how Nsight made it very easy to identify these particular issues. We used the shader debugger to set breakpoints in our shaders, inspect values, and set watch variables. And we use the API Inspector to see a high-level overview of multiple draw calls at once, to see how each particular uniform was set for different passes, and to trace that back to why we weren't seeing quite the dynamic tessellation that we wanted to with our shader. So what I'm going to do right now is I'm going to jump into the next scenario we have for you. Okay. Just give me a moment to load that up. Sorry. I apologize, I'm opening up the wrong scenario. Okay. Okay. So what we have here is what I'd like to show you here is some of the constants we're using for the FFT. Now, for those of you who are not familiar, an FFT is a fast Fourier transform. It's basically a conversion from the time domain to the frequency domain. I mentioned earlier that our FFT was using a 128 by 128 resolution map. Now what I'd like to do is I'd like to take a look at what sort of performance we're getting with this particular map. And then what I'd like to do is I'd like to see if we were to increase the resolution of this map, what would our performance be? So I'm going to first start by building the application and starting debugging with 128 by 128 map. Okay. You can see on my launched application that my application is running at about 230 frames per second. Also important to note is that the GPU is at about 90% utilization over here, maybe somewhere between 80 and 90%. Let's take a look at what happens when we actually up that to 512 by 512. I'm going to update my code, rebuild my application, and relaunch. Okay. So, in changing that to a 512 by 512 patch, we went from about 230 frames per second down to about 15 frames per second. Now that's not good at all. Also very important to note is that our GPU is hovering at about, I'd say around 7% utilization, and that's not good at all. While we're having a much higher detail image, our GPU is just left starving by the fact that this CPU-based FFT is just bottlenecking the entire application. So one thing also to note is that our reflections don't look good at all in this 500 and 512 map. It's really, we have way too much saturation and it looks very blocky. It's kind of an all or nothing reflection over here. So we want to make sure that when we do fix whatever bugs we're going to fix right now, when we move this over to the GPU for increased performance, we try to take that into account as well. So what I'm going to do is I'm going to be moving over to the next scenario here. And what we've gone ahead and done is we've gone ahead and implemented this FFT on the GPU. Having done that, though, what I'd like to do is I'd like to see what sort of performance we're getting. I'm going to start graphics debugging one more time. Okay, so we clearly have a bug here. Our water isn't even being rendered at all, that is to say. So let's try to enter pause and capture to see what's going on here. So I'm going to bring up the HUD and I'm going to attempt to pause. I get an error message over here that's telling me, you can see it in the lower right hand corner here, that I cannot enter frame debugging because it says that Nsight only supports frame debugging for OpenGL 4.2. The particular function that's suspect, it's fading away on me. The particular function that is suspect is GL text subimage 2D with a format of 2002 and a particular type. Now, GL text subimage 2D is of course supported by Nsight. So let's see what's going on here. Maybe we have something. Maybe we have an error in the way that we're actually making that call. So what I'm going to do is I'm going to search for where we're using this particular call. I'm going to search my entire solution for GL text subimage 2D. Okay. I see that they're all in this GPU water file. Okay, two right by each other. As I mentioned before, the suspect parameters here were the format and type. Now I should mention why we're actually flagging an incompatibility over here. GL is made up of many extensions, and in order to ensure that we can capture an application correctly, we need to make sure that we support that an application is only using the extensions that Nsight supports. Now Nsight supports quite a number of extensions, but OpenGL is constantly evolving, and we need to make sure that when an user is or an application is using something that we don't support, that we don't introduce the bad information by running into errors. So what I'm going to do is I'm going to take a peek at these particular formats, these particular calls here, this GLR format and GL float. So I'm going to go to definition to see what this particular format is supposed to be. Now this is odd. This doesn't look like a format at all. Actually, these particular enumerations are texture coordinates. Now that's not right. Let me inspect the next usage of this. GLRG. Okay, so now I'm seeing some actual texture formats. I see GLRG, GLRGB below. Okay, here's the problem. Where the application programmer specified GLR when in fact what we wanted was GLRed, basically a single component vector. So I'm going to update my code here. So this is very understandable. This is sort of a wrinkle in the way that GL implements enumerations, but the Nsight's capture incompatibility actually helps us out here by pointing us directly to an application bug. So I'm going to rebuild the application and try it with that fix in place. Okay, so we still, even with this fix in place, we don't have any water. Let's see if we can figure out what's going on. I'm going to try and capture like I did before, and hopefully I won't have any capture incompatibilities. Okay, so I can actually successfully capture. What I'm going to do is I'm going to scrub to the draw calls that are implementing this GPU-based FFT. And I'm going to scrub to this call 22. I'm going to switch over to Nsight. Now you can see that this particular call over here is in this GPU water pass over here. So what I'm going to do, like before, is I'm going to open up my program view and I'm going to link to my shader debugger. I'm going to click through to my fragment shader, which is implementing this FFT. And I'm going to set a breakpoint within this particular function, the shader I mean to say. I'll just set it right at the end. Wait a moment for the breakpoint to be hit. Now what's odd here is that the breakpoint just isn't being hit. That's not right. We showed before that the shader debugger was working. I wonder if this call is actually even being executed at all. Let's take a look at the program page. I can see that the link status for this currently bound program is true, meaning that we linked successfully. So there's got to be something else going wrong. Let me see if I can take a peek at the geometry that I've configured for this particular call. I'm going to go to my geometry window. Just going to put it right over here in the middle. And I have no geometry. That's not right. Something else is wrong here. But let's take a look a little bit near the beginning of the pipeline. Let's start right at the top, at vertex specification. So I see that I have one vertex attribute for this particular VAO, and I see that, okay, well, this particular vertex attribute is not even enabled. Okay, so that's a pretty clear error. We have to go back and enable this vertex attribute before drawing in order to use it. So I'm going to search for where we configure this VAO and specify this particular vertex attribute. This happens in our GPU water code, and I'm going to move over to where we're doing that. I can see that we're generating the vertex array, we're binding it, we've even configured it, but we haven't yet enabled it. So I'm going to add a call to enable it. And that particular call is GL enable vertex attrib array. It is the 0th element. I'm going to save, rebuild, and I'm going to run once more. Okay, so we have water this time, but it's clearly not right. It is kind of cool looking, but it's not right at all. Let's see if we can figure out what's going on. Given that we've, made this port from the CPU to the GPU, I'm going to suspect that there's something wrong with the GPU implementation. So let's take yet another look at it. I'm going to pause and capture my application. I'm going to tab over to my host. By the way, Nsight works tremendously well with multi-monitors. Unfortunately, we only have one monitor for this webinar, but if you have two, it's often really great to have your application on one monitor and your Visual Studio instance on the other. And I'm going to scrub over to the first draw call in the GPU water space region. What I'm going to do is I'm going to set a breakpoint in my fragment shader. Again, going over to my program, linking over to my fragment shader, and I'm going to set a breakpoint here. Wait for that breakpoint to be hit. Okay, it is being hit, so we know we fixed our issue that we were having before. I'm going to step through with F10. Okay, I can step through this particular code. So I can go through and I can inspect each particular value, each particular variable value as I'm stepping through. But what I'm actually interested in is I'm going to take a look at a different pass of this algorithm. This particular algorithm uses multiple passes. So what I'm going to show you now is how to set a conditional breakpoint with Nsight in the same way you would with Visual Studio's normal debugger. I'm going to right-click this breakpoint and set a condition for it. The condition I'm going to set is for pass greater than 0 so that I can see any pass other than the first in this multi-pass algorithm, and I'm going to resume. I'm going to wait a moment, and I'm going to see that this particular conditional breakpoint is never hit. Wondering if this uniform variable of pass is not updated in the way that we want. Okay. Let's see if I can go to the API Inspector to figure out what the value of this particular variable is. I'm going to go to my fragment shader here. I'm going to see that I have my active uniform of pass down here, and its value is currently 0. I'm going to scrub through and see how it's changing as I issue each particular draw call. And I can see that as I'm scrubbing, pass is unmodified in this horizontal pass of the FFT. Okay. Now this is my vertical pass, and I can see that it's going from 0 to 1 to 2 to 3, 4, 5. Okay. So that was the forward FFT. Let's take a look at the inverse. Back on the horizontal pass, 0, 0. Again, if I'm looking down here at this pass variable, seeing, okay, it's starting to climb back up as we would expect. Okay. So somehow this particular pass variable is not being set correctly in the horizontal pass of my FFT. Let's see if I can figure out where this is being set. I'm going to stop debugging for a moment, and I'm going to go back to my code. My code is gpuwater.cpp, and I'm going to search for this pass variable. Okay. I see here on line 261 that the horizontal FFT program locations pass variable is set. I'm looking up the uniform location for this particular variable in the vertical FFT program. That doesn't sound right. In the vertical FFT program, I'm looking up the uniform in the vertical one. Okay. This looks like another copy and paste bug. We should have been looking up in the horizontal FFT program over here. So I'm going to make that change and see what happens. Okay, I'm going to rebuild. I have some build success, and I'm going to start graphics book debugging one more time. Okay, we're getting what we want. I am now running this 512 by 512 FFT on the GPU. The water looks great. You can see that my performance has climbed from before, when it was about 20 frames per second, to about 100 frames per second now. My GPU utilization is at 90%. So basically, when we started, my GPU utilization was at 90%, but that was with a 128 by 128 resolution map. Now that I've moved to a 512 by 512, I haven't really changed my GPU utilization at all, but in shifting that algorithm from the CPU over to the GPU, I've increased my performance substantially at the cost of some frame rate, but I'm still quite high. So that is very good. Let's take a look at what we looked at in this particular example. I'm going to stop debugging. Go back to my slides. Okay, again, I mentioned that we converted the wave generation from CPU over to GPU. Along the way, we did encounter some bugs, but we showed how Nsight can be used to help you identify these bugs. The first issue we found was a capture incompatibility, and this was actually sort of a lucky way of encountering a bad app. And what the next particular one we have was to find a missing enable for the vertex attribute. That was when we weren't drawing the water at all when we had captured. We then, upon fixing that issue, we had those weird waves, but we jumped in with the shader debugger and found that we were not actually setting a particular uniform variable as we expected. And we used incredibly powerful conditional breakpoints to show you that. So running at about 512 by 512, I have in my slides 180, and that's not correct. I think we've changed the GPU that I'm using in my system, but it's actually closer to 100 frames per second. But our GPU utilization is in fact at 90%. So I'm going to go over to the next scenario that we have. Let me just close out the other one so I don't get confused. Okay. going to build my application. Now basically this scenario has all of the fixes that we've introduced since we started, and I'm going to basically start here and take a look to see if there's anything else that we want to improve in this application. I'm going to launch graphics debugging one more time. Okay, so yes, we have this great looking waves, except for this reflection over here. It's kind of an all or nothing reflection. It's way too blocky. We do have the frame rate we want. Our GPU utilization is good, but let's see if we could do something about that reflection. Well, first off, let's see how this is actually being calculated. What I'm going to do is I'm going to pause and capture my application. And what I'm going to do is I'm going to switch over to Visual Studio. Now I'm going to show you a window here that I haven't yet shown yet, which is basically a view of all of the resources that you're using in that you have created in your application. To do that, I'm going to go to the Nsight menu, Windows, Resources. I'm going to dock this conveniently on the right-hand side. And what this resources view shows you here is a view of all of your textures, all of your buffers, with a little thumbnail that describes each particular resource. We have the ones I'm interested in right now are drawables, basically the default drawables. I'm just going to collapse some other things to make it a little bit more easy to see. And one of the most powerful features that this particular resources view shows you is it shows all of the revisions that this particular resource has seen within a frame. You can see that on the bottom over here. I have all of my available revisions that have all of the revisions that this particular resource has seen. And in this frame, this is seen 28. So what I'm going to do is I'm going to look at a graphical view of this particular resource, and then what I'm going to do is I'm going to use Nsight's pixel history view to see what draw calls are actually contributing to this highly saturated pixel. To do that, what I'm going to do is I'm going to do select pixel, and I'm going to pick one of these saturated pixels, and we run a pixel history here, just expanding this so that everybody can see. And I can see that there are 5 draw calls that are contributing to the value of this particular pixel. Now, there's 1 clear and 4 draw calls. What's really powerful about the pixel history is that it shows you a progression of the color value of this particular pixel at over time. We can see that we start off clearing it to a blue. In our first draw call, we end up with a white, and in our second draw call, we can see that the fragment that gets blended into this pixel is actually quite highly saturated here. You can see that the RGB values are at 14. Now, I misspoke a second ago. I said the second draw call. What I should have said is that both of these are within the same draw call. Both of these fragments are contributing to this particular pixel, and the highly saturated one is essentially what is landing. So these highly saturated values are not desirable at all. This is what's causing us to have this really blotchy, very all or nothing reflection. Let's see if we can figure out why this is happening. Now, what Pixel History offers is a great link to basically select exactly the shader and program that is coloring this particular pixel, and create a conditional breakpoint so that I can break in the shader debugger at exactly the draw call and fragment that is causing this particular that results in this particular value. So I clicked that debug pixel link, and I'm brought right to the start of the evaluation of this shader for this particular pixel. What I'm going to do is I'm going to move this breakpoint down to a place where I can actually see where the color values are being set, and I'm going to set its location somewhere down. I have in my notes to line 233. Okay. Basically, this is we started off with the evaluation of the various constants for this particular, or variables for this particular shader, and this is just a compiler bug. Ideally, we'd start it at main, but it's really a very easy issue to work around. I set my breakpoint to the end of this function, and I'm going to actually, let me move it to line 229. Okay, I'm going to resume. Now one thing I should show you by hovering over this breakpoint is actually the quite complex conditional that is automatically created when we did this debug pixel link. You can see that it's inspecting both pixel location, draw call ID, etc. And what's really powerful about this particular conditional breakpoint is that all of this is evaluated on the GPU for very, very fast evaluation. Okay, I'm going to set a watch on this particular color variable. Let's see. Okay, we start out. Oops, I should pin this particular window. Okay. We start out with color, the Y component being non-zero, all other components are 0. I'm going to step over this particular line. And I can see that my value is still unchanged. Okay. So it seems like we actually have an issue in the watch window. It's not showing the correct value here, but what is important to see here is that this water specular intensity is actually quite high. All of the other factors are somewhat reasonable, but this water specular intensity is quite high, and the watch I've set is not actually reflecting this value correctly, but I am getting my inputs correctly. So I think that this must be what's causing those highly saturated pixels. Let's see if I can figure out where this particular variable is set. I'm going to stop debugging, and I'm going to go to my shader, and I'm going to search for G water specular intensity. Oops, typo. Okay. It's set to a constant 350 here. Let's see if we can cut it in half and see what this actually accomplishes. Let's cut the power as well. Okay, I'm going to run one more time. Okay, so now that looks a whole lot better. Whereas before we had this very blotchy specular reflection, we now have a much more dynamic reflection. And where we are ending up here is we've got this 512 by 512 map generating a water. We're still running at 100 frames per second. Our GPU is highly utilized, and we are basically have achieved all of the algorithmic improvements we were looking to achieve throughout this example. So what I hope you had a chance to appreciate today is all the powerful features that Nsight offers for OpenGL debugging between our integration of the shader debugger and API Inspector, inspecting uniform values, seeing draw call state, using pixel history to see how a particular pixel has changed over time, etc. So what I'd like to do right now is open the floor up to questions. I haven't gotten a chance to see what questions may have been asked already. I know Jeff has been working hard to answer any questions that anybody has had, but I'd like to open up the floor to additional questions if anybody has anything that they'd like to bring up right now. For those of you that aren't familiar, GoToWebinar does have a question box that you can type into to ask your questions. Okay, so
you know what, I'll go ahead and read off just a few of the ones that came up along the way. Appreciate all the questions. I hope I answered them all properly. It's my first time with GoToWebinar, so I hope I got it right. A couple of the big ones that came up were questions about, for instance, do we support Linux? Do you want to comment on that, Dan?
Sure. So the question is, do we support Linux? And this is something that we're considering. You know, this is something we're always looking at. What platforms and what features are most valuable for our developers. So this is something that we're hearing from a number of people, and we are actively considering.
We just had a question from Lewis. Was asking if there's a special driver required to enable Nsight debugging.
So we do specify a particular driver version with each particular release of Nsight, and for features like Shader Debugger, we have a very close interaction with our driver. So while there is no real special driver, it is a production release driver. You do need to have a fairly up-to-date driver when updating your version of Nsight.
Great. Next question was, does the entire app have to be core, or can some of the modules be mixed and matched, some core, some not core?
Sure. I'm assuming by core you mean to say, does the entire app need to be OpenGL core? Now, we actually support, we fully support OpenGL core 4.2, but we do support quite a bit of compatibility, and we do support quite a bit of other extensions. So what's really a question of is what functionality is your app using, and whether or not there's anything that you're using that is unsupported by Nsight. So we have in our release notes a list of all of the extensions and features that we support. I apologize, I'm getting some feedback into my mic. It's making it hard to speak. But so the answer is you do not have to be fully core in order to use Nsight. Now, if you do use features that we don't support, unfortunately we have to trigger a capture incompatibility because we don't want to present bad information. We basically can't enter capture in that state. However, I will mention that you can use remote shader debugging. So if you have two machines, you can hook one up to the other. I mean to say, you can launch an application off of your development machine on a target machine and inspect in the same way that you would with an actual running application. And really the reason for the remote target is so that we can pause the GPU.
And also note that all of our tracing features also work in spite of not having OpenGL 4.2 core.
Yes, absolutely. I forgot to mention that we have a performance analysis mode, and while I mention this, I should mention that we do have another webinar next week. I believe it's next Thursday, where Jeff will be discussing all of the performance-focused features that Nsight has, and one of them is application tracing, and that is fully supported across all of OpenGL.
Great. Jorge, if I pronounce that correctly, seems like he had an issue installing, when he installed onto a system that had both Visual Studio 2010 and 2012, it wasn't showing up in 2010. Jorge, I encourage you to email us at devtools_support@nvidia.com. We haven't heard of any problems with that, but we can maybe get some logs for you and try and figure out what problem is going on there. It should work just fine. That's exactly what we have set up here, so surprised to hear that. Looks like Sebastian had a question about CG shaders. Actually, NVIDIA in general has deprecated CG, so we're not really supporting that at the moment. But if you can translate those into GLSL, you should be fully supported there in Nsight. There was a question about the having the presentation available on the web. Nadeem, could you read back that website that this can be available on again, please?
Sure, I'll be happy to. I'll shoot it over on the chat window so everybody can see it.
Great, Nadeem will put that on the chat window. Thanks. And thanks, Daniel, for the props there, and Bob. I guess a couple other questions we had were, do you support mobile devices? We are actually working on our next generation tool for mobile devices. You probably heard some of our new SoCs that have basically full desktop powered GPUs on them, and we are actively working on the tools for those. Look out for it sometime early next year for you ES developers out there. Any other questions or concerns? Great. Thanks everybody for coming. We've had an absolutely great time. Thanks, Dan, for doing such a great job on the presentation. And again, we look forward to seeing you next week at same time, same bat channel at Nsight Visual Studio Edition for performance analysis.
Thank you.